In the presentation of the phenomenology of bifurcations, I mentioned in particular the three cycle. And because it's so beautiful and interesting, I'd like to focus on it a little bit more. So let's discuss the dynamics of the three cycle. So to look at the three cycle dynamics, what we need to do is plot xn plus 3 as a function of xn. So we have to take the third iterate of the function f of x. So this third iterate is a function with 4 humps for a just beyond the birth of the three cycle, which is 1 plus the square root of 8. So it's a 4-hump function, so it looks something like this. This is the unstable fixed point of the 1 cycle. We have an alternating series of stable and unstable fixed points of the 3 cycle. So let's call these points xa, xb, and xc. So these 3 points, xa, xb, xc, define the 3 cycle. So once you're on a 3 cycle, you stay there. And let's look at the stability at the fixed points. And so once again, let's look at the derivative of the function on the 3 cycles. So let's look at f third iterate, for example, of xa prime. So when I differentiate this, I'll get f of x prime, and then doing the chain rule of calculus, this is nothing more than f prime of f of x times f prime of x times f prime of x. And so if I start at point xa, so here we have f prime of xa. On the 3 cycle, when I'm starting at xa and I take f again, I'll go to xb, for example. So this is f prime of xb. And then at xb, the second iterate of xa, that'll take me to xc. So this is f prime of xc. So once again, we see that all 3 points on the 3 cycle, xa, xb, xc, the derivatives are all the same. And so when 1 point is born, 3 points are born, and they're all the same relative stability, they all become unstable at the same point. Now, if we look at a little bit more detail, let's now imagine looking where a is just less than 1 plus the square root of 8. So in this case, our function, our iterate function, looks something like this. So the point is that there's still the one unstable fixed point, but now you see that the function does not touch the 45-degree line. Let's take one of the branches of this iterate function, and it looks something like this. Barely misses the 45-degree line. So we ask, how does x evolve very close to this type of point? So if I have a value x naught, I go up to the function, then I go to the 45-degree line, up to the function, 45-degree line. And you see that I stay stuck in this little narrow opening, and then finally, after a while, I go off far away. So this region, where the third iterate of the function is almost stable, might be called smooth behavior, but then it's punctuated by periods of time where I run far away. And so the dynamics is, roughly speaking, close to this point, which is called the tangent bifurcation. The behavior of the iterate is relatively smooth because it barely moves, and then after a while you go off far away until you come again close to a tangent bifurcation. So this type of behavior, where the system is smooth behavior for some period of time and then runaway behavior, is called intermittency. And this is the basic feature of the tangent bifurcation. So it's a very different type of bifurcation compared to the period doubling because it has this phenomenology of intermittency.